This video is about trigonometric ratios, and by the end of this lesson, you should understand that by similarity, side ratios in right triangles are properties of the angles in the triangle, leading to definitions of trigonometric ratios for acute angles. We'll define what those ratios are, give them some names, and also talk about how to use them, and the next standard, SRT 8, use those ratios to solve right triangles in applied problems. Let's get started. Let's start at the bottom of page 164. In this problem, number 10, Serena is trying to measure the height of her building. I'm assuming it's her apartment building. And she knows the distance that she is standing away from the building, and she knows the angle of altitude. So what the angle is from the ground up to the building. And she's trying to figure out what the height of that building is. Now, the fact that we're incorporating angles, the exact angle measure is a new thing for us. Before we've looked for similarity, we've done things with the Pythagorean theorem, but now we're using just one length and an angle to figure out the height of this building. And we'll come back to this problem, but that's kind of where we're going in answering these questions today. So before we get into answering that question, I want to go back here and talk about how to define. Here I'm now on page 161. So in these problems, I'm not sure why that bottom line didn't show up, but here it is. So for each exercise, label the appropriate sides as adjacent, opposite, and hypotenuse. And this will all make sense a little bit later as we define these trigonometric ratios. They use within figure ratios of adjacent to the angle, opposite of the angle, and the hypotenuse of the triangle. So for angle F, and it's always with respect to one angle. So with angle F, the adjacent, which means next to, the leg adjacent to the angle is FD. The leg opposite the angle is on the opposite side from the angle, and this is the opposite leg. And finally, the hypotenuse is the hypotenuse of the triangle. And it's really important that you get comfortable with naming the adjacent to the angle, the opposite the angle, and the hypotenuse of the triangle, because we use those labels in our within figure ratios that we'll be defining a little bit later on in this video. In number 5, the angle's over here, but we still have the leg adjacent, not the side adjacent, but the leg that's adjacent to the angle. I'll abbreviate ADJ. And the leg opposite the angle and the hypotenuse of the triangle. Okay, let's try one more. For angle K, the leg adjacent to the angle is this one. And the leg opposite the angle is on the opposite side. And finally, the hypotenuse of the triangle is this one, which is always across from the 90-degree angle. Okay, now let me jump to a Geogebra file and talk about why those angles are so important. This is a Geogebra file that I made, and we're focusing on angle A, the angle down here. And I picked the same exact angle as Serena measured to the top of her building, but I've labeled again that this is the leg adjacent to the angle, and this is the leg opposite the angle, and this is the hypotenuse of the triangle. Now I've measured those in GeoGebra, and I've also found some ratios over here. So I've taken, at least GeoGebra has taken, the opposite length and divided by the hypotenuse length and came up with a ratio of 0.7. Now it's rounded off quite a bit, but this will be enough to see the pattern that I want you to see. We've also taken the adjacent length, 4.8, and divided by the hypotenuse length, 6.3, and we get the ratio of 0.8. And finally, we looked at the opposite length, 4.2, and divided by the adjacent length, 4.8. Now, I'm going to erase some of this because the numbers will change a little bit. Now, I want you to notice something, that first of all, angle B has been constructed to be a 90-degree angle. So even if as I move this, angle B will always be a 90-degree angle. I want you to first notice that the side lengths of, the three side lengths of this triangle are changing. But please notice over here that the ratios are not changing. Okay, now just, they can change, right? So this is dynamic, so it can change, but, if I change B, only those numbers don't change. Okay, now why would that be? I'm hoping that we've done enough with dilations, enough with similar triangles, enough with things that you recognize that by the angle similarity criteria, that as I change B, the 90-degree angle of all of these, actually infinitely many triangles that are looking at, for all of these triangles, B will always be 90 degrees. And angle A, as long as I keep that to be the same number, whatever number that may be, that all of these triangles, this triangle, this triangle, this triangle, all these triangles will be similar to each other by the angle similarity criteria. And so all these within figure ratios will all be the exact same number. Now, if I change C, and this angle A, begins to change, then they're no longer similar to each other, because I only have one angle B, that's the same. And so you'll notice that all of these angles over here, all these ratios, we say, are changing. Okay, that is the key to understanding today's topic about trigonometric ratios. These are all trigonometric ratios. They're ratios within triangles, specifically right triangles. And as you have the same angle, the ratio will be the same. So at this point, I'm going to name these three ratios. They have a name. They each have a name. And the name of the opposite leg divided by the hypotenuse is called the sine ratio. The name of the adjacent leg, the length of the adjacent leg divided by the hypotenuse, has the name of cosine. And we'll talk, I think, in the next lesson about why this is called the sine and why this is called the cosine. Okay, we'll talk more about that in a future lesson. I think it might be the next lesson, but we'll talk about the relationship between the sine and the cosine. But for at least for now, know that opposite of a hypotenuse is the sine ratio, the adjacent over the hypotenuse is the cosine ratio, and the opposite over the adjacent is called the tangent ratio. Okay, now there's a nice acronym that I like to use to remember which ratio is which, and it involves using the first letters of all of these. And the mnemonic is SOHCAHTOA. SOHCAHTOA. So if you take so, ka, toa. SOHCAHTOA. And that helps you know that the sine ratio is the opposite length divided by the hypotenuse of the triangle, and the cosine ratio is the length of the adjacent leg divided by the hypotenuse, and the tangent ratio is the opposite leg divided by the adjacent leg. Okay, so those ratios have names, and back in the day, before calculators, BC, there used to be tables of them, but now they're actually programmed into our calculators. So let me walk you through a problem where you can find the sine, cosine, and tangent ratios using your calculator. Okay, let's go back to Serena and measuring the height of her building. Okay, now, Serena wants to know the height of the building, which I actually draw on this side, because that's the part of the triangle. She wants to know the height of the building, which from 41 degrees is the leg opposite the angle. And the information that she has, what she knows, is the adjacent leg, not the hypotenuse, even though it is also adjacent. It's the leg adjacent to the angle. Now, I've taught geometry enough to know that my hint to you is do not label the side that you do not care about. Okay, in this problem, I don't care about the hypotenuse. Okay, you could write in hypotenuse, but please don't. If you don't write in hypotenuse, it is much easier to see which of the three ratios you want to use. Now, our mnemonic is so, ka, toa, and I want to know the opposite, and I know the adjacent. So that is opposite and adjacent are only related in the tangent ratio. So the most useful ratio for Serena is the tangent ratio. And the tangent of 41 degrees is equal to the opposite length divided by the adjacent length. Now, you can use your calculator to find out the tangent ratio. But before you do, understand that there are two ways to measure angles. Okay? The way that you're most familiar with is called degrees. There is another way, which is called radians. And now, unfortunately, many calculators have their default setting in radians, and so does graphing calculators. So make sure you check that. On a graphing calculator, you will type in tan parenthesis 41. So on my graphing calculator, I put tan 41, which I know you can't really see on the screen, but that's what I'm doing. And I find that the tangent ratio for an angle of 41 degrees will be 0.869. Now this is equal to y divided by 120. Now, the way that I recommend solving this is by using all the skills you've learned about proportions by taking that ratio and dividing by 1, which doesn't change the value of that, but by making it look like a ratio, it's very easy for us to then cross multiply and find the missing length. So 1 times y is y, and the ratio 0.869 times 120 is equal to 104.3 meters. And that is the height of Serena's building using only the distance that she is standing from the building and the angle of 41 degrees. This lesson was about trigonometric ratio. We defined the sine ratio, the cosine ratio, and the tangent ratio using properties of similarity, and we use those ratios to solve right triangles in applied problems. Thank you for watching.